Hello friends, welcome to another lecture on Insight classes. In this lecture, we will be calculating maximum gain for a system using RH criteria. This gain will be the gain for which the system does not become unstable. And third, we will be calculating frequency of oscillation when the output is oscillating. Now moving forward our lecture, we will see how to calculate the gain value of a system. Consider a transfer function GS. Now suppose that this GS is a part of a closed loop system in which there is a controller whose gain value is K. Now remember, since K is a gain value of the controller, it has to be greater than 0. That is, it is a non-negative number. For the closed loop system, we will get the transfer function as GS upon 1 plus GS. So our characteristic equation will be the denominator of this transfer function. You can see that we have obtained this characteristic equation with a value K here, which is the gain of the system, and we do not know this value, and we will try to find this value using RH criteria. For this characteristic equation, we will calculate the RH matrix, and we will continue with our calculations as we have done for earlier cases. Now here remember, since there is one unknown value, the terms might get a little bigger, so it is a good practice to separate the rows a little more and to separate the columns a little more in for these cases, so that it is easier for you to calculate and populate the values. Having completed the calculation, you can see that in the first column we have three terms with value k. And remember, for the system to be stable, all the elements in the first column should be positive, and we will use this specific feature for finding the limiting value of k. Now for the system to be stable, we want this term to be greater than 0. We will take the first element with k and we will make it greater than 0. By calculating, we get that when k is greater than minus 238.875, these values are positive. But earlier we have discussed that k is a gain value and it cannot be less than 0. So this element will be positive for any value of k greater than 0. Now let's take the second element using the RH criteria that all the elements in the first column should be greater than 0. So for this system to be stable, even this term should be greater than 0. We will solve and simplify this, and we will see that we will get a quadratic equation. On factorizing this term, we see that there are two roots for this. One is a positive root, that is 8.697, and second is a negative root, 2636.7. Since k is a gain value and greater than 0, so this second condition will not apply to our system. Hence we will be using only the first condition, that is k should be smaller than 8.697. Now for the third element, that is only k. For this element to be positive element, k should be greater than 0. So here we get the range of our k, where k should be a value between 0 and 8.697 for the system to be stable. To understand this, let's take an example. When k is greater than 8.697, the first element will be positive, but the second element is negative, as we have seen in earlier calculations. So there are two sign changes here. It means there will be two right hand side poles, and thus the system will be unstable. For value of k smaller than 8.697 and greater than 0, we will see that all these three elements are positive. Therefore, there are no sign changes in the first column of the RH table and the system is stable. Now, in the case when k is equal to 8.67, the first value is positive, the second value is positive, but the middle value is 0. Since there is only one element in this row, we can see that there is a all zero row condition when k is equal to 8.697. Now, as we have seen earlier, when we have no sign change in the first column and we have a all zero row in our RH table, we need to factorize the auxiliary equation. Here, the auxiliary equation will be based on s raised to power 2 row, where the value of k will be 8.697. So we'll calculate the auxiliary equation here, factorize it and find the roots. On calculation, we can see that the root is 0.7869 and it is a non-repeated root. Hence, the system is marginally stable. And the oscillations of this output will correspond to these roots. That will be the value of oscillation will be 0.7869. Let's see the pole zero plot as well as step response for each of these three conditions. The first condition, when the k is smaller than 8.697, here we will suppose that the k value is 5. And we'll plot the curves. You can see in the pole zero plot that there are two imaginary roots, and both of these roots are just on the left hand side of the imaginary axis. Hence the system is stable. And from the step response, you can see that there are some oscillations in the beginning, but later the system becomes stable. For the second case, that is k greater than 8.697, we'll assume a value of k equal to 10. Now here in the pole zero plot, you can see that the imaginary poles are now on the right hand side of the imaginary axis. Thus, the system is unstable And this is confirmed by the step response where we can see that the oscillations are continuously increasing to a very high value. Now we will take the third case where k is equal to 8.697. Here in the pole zero plot you can see that the poles are lying on the imaginary axis and the step response is fairly oscillating. In the step response for k equal to 8.697 you can see that the oscillations are slowly decreasing. This is mainly because the value 8.697 is an approximation. The actual root might have some more decimal points. If we use the exact root value, we will get a perfectly stable oscillations. But since here we have used an approximate root, we are getting a slight decrease in oscillations over time. If you like the video, please subscribe the channel and share it with your friends. Thank you.